All right. Welcome to this episode or this lesson of study of mathematical proofs, and we are still on what we call mathematical induction. And I'm going to solve two other problems in this video. I hope I'll be able to solve them within 20 minutes and or maybe less. Yeah, that's what I'm thinking of. Um, yeah. So after proving this and the other one, then we'll jump to maybe another you know um, tool that we need to write mathematical proofs. So we'll definitely go to what we call proof by contrapositive and the rest. Okay, so yeah, so with this particular problem, we have a proposition given to us that for all integers n greater than or equal to 0, 10 divides this guy. You realize that most of my problems that I'm solving are indeed about something divides something, something divides something. Those are really something that most students find difficult to get it. And after that, I will actually solve a different problem that is not in terms of derivation. Okay. So with this, to prove this, I'm going to use mathematical induction. And I don't know if probably that there will be other ways to prove this, but I'm going to use mathematical induction. And this falls under what we call the strong inductions. And I said for strong induction, you need more than one base case, most of the times. But you don't really get to know the base case before, so all you have to do is apply the first principle of mathematical induction, prove this, and when you are done proving, you can go through your proof again, and if you see there is something that is not right mathematically, then you fix that, and in fixing that, you get to do other base cases as well. All right, so with this, what does this mean? This means that when we say that 10 divides n to the fifth minus n, this implies that n to the fifth minus n can be written as some 10 multiplying a constant, let's say b, right? So that is the idea. Now, let's start with the base case. The base case is that n is starting from what? N is greater than or equal to 0. So when n equals 0, what happens? Let's assume that our p of n is such that 10 divides, that. So p of 0 is such that 0 to the power 5 minus 0. Okay. And this is equal to 0, and that is the same as 10 multiplying some 0, right? 10 multiplying 0 is equal to 0. So in here, 0 is b. So this claim is actually true, that 10 divides 0. Actually, any number apart from 0 itself divides 0. Any number can be written as 0 multiplying something. Don't try to argue that 0 is equal to 0 multiplying 0, because if you do that, it means then 0 divided by 0 is actually equal to 0, which doesn't make sense, right? It's not really right in mathematics. So yeah, if you have this, that the base case is also true. I said in mathematical or strong induction, you need other base cases, but for now, let's assume that this is the only base case we know, and when we are done proving it, the other base cases will come. Now the inductive step is that you try to show that how do you call it, for any k that is greater than or equal to 0, okay, p of k is true, which means that k to the power 5 minus k can be written as 10 multiplying some b, right? Now you consider k plus 1. Consider k plus 1 to the power 5 minus k plus 1. And this is when n equals k plus 1, right? So you can, more appropriate, you can start with consider n equals k plus 1. Then what can you say? When n equals k plus 1, we want to make sure that k plus 1 to the power 5 minus k plus 1 can be written as 10 to the 10 multiplying some constant b. Okay. And with that, I said that you have to try to argue with this. And trying to argue this comes with a lot of work here, but we'll do that. Let's try to make sure that since we have 5, the power 5 here, let's try to make sure that we can write k plus 1 into some, sum of choose expression that when I expand, I will get multiples of only 10. Now, you can do that by considering the factors of 10. The factors of 10 are 1, 2, 5, and 10 itself, right? But notice that if I put 5 here, right, I want to write it as k minus something plus one of these guys, one of these factors. I can't put 10 there because I can. The easiest one you can do is to actually put 10 there. I think that should be the easiest one to do, but it's going to cost you a lot because if you want to put 10 there, it means you're going to use a lot of base cases here. Trust me. Because if you want to put 10 there, then k plus 1 is the same as k minus 9 plus 10, right? This is what we are interested in. It means, at the end of the day, don't worry, I'll get there. We'll have to find some number of base cases, and the number of base cases comes with the number you subtract from k. So the one that I did, if you're supposed to go by that, and you're supposed to do 9 base cases, which we don't want that. Now let's pick. Ideally, when I use 2, it's going to work, but you can actually try to use any of them. I mean, if you use 5, it's not going to work because this is the same as, look at here, this is k minus plus, or maybe minus something, k minus 1 plus 2, and this is going to give you k plus 1, right, to the power 5 minus k minus 1 plus 2. This is true, right? Because I can express this guy as k plus 1, that guy as k plus 1. And I said this plus 2 is coming from the factors of 10. Now, what I want to do is that we are assuming that for p of k, it is true, So if you move all the way from k equals 1 all the way, I mean, starting from n equals 1. Did I say 1? I'm sorry, k greater than or equal to 0, so it means all the way greater, anything that is greater than or equal to 0 all the way to k, it is true. It means k minus 1 is actually less than k, right? But we know p of k is true, and we assume that every one of the k's, anything below k all the way to k is actually true for this argument. So this guy can be written as maybe some L plus 2 to the fifth power minus some L plus 2. Notice that L is equal to k minus 1, and indeed 0 is less than or equal to k minus 1 less than k, right? K minus 1 is actually less than k. So it means the claim for p of k minus 1 should be true. P of k minus 1 should be able to, that is going to be p of L, because L is equal to k minus 1. And so we should be able to write L to the power 5 minus L to be 10 multiplying something, because it's less than k. P of k is true, and anything that is below p of k, or maybe anything that is below k, any number that is below k, p of that number is actually true. So that's the argument we're going to use here. Now let's do this. Alright, so this guy, if I expand it using Pascal's triangle, you can try to make sure that you understand how to, if you follow my previous 2 videos, you know how I'm going to write the coefficient, but I guess I just want to write this straight away. So if I expand this guy, it's going to give me L to the power 5, plus 5 multiplying 2, L to the power 4 plus 10 multiplying 2 squared, L to the power 3 plus 10 multiplying 2 cubed, L squared plus 5 multiplying 2 to the power 4, L, what do I have again? Plus 2 to the power 5. That's the first expansion. All of these minus L minus 2. Right. Now if I go ahead, I'm going to have that k plus 1 squared. Did I say squared? 5 minus k plus 1 is equal to, we've been able to express it in terms of L. So this guy is going to be L to the power 5 minus L. I'll go back and show that to you. 10 L to the power 4 plus 10 2 squared, and that is 4L cubed plus 10 2 to the power 3, and that is 8 L squared, and then plus 10 multiplying 8 L plus 32 minus 2. If you go back, 5 multiplying 2 is 10, 2 squared is 4, and this is 8. You know, this is 5 multiplying 2 to the power 3. So these guys, when you multiply them, you have 10 multiplying 8. I have something like that in there, and then 2 to the power 5 is 32, then minus this 2, and then if you realize the first two terms I wrote L to the power 5 minus L. So sorry, where did we go? Yeah, so this is what we have. Now, having this guy here, we know that anything that is below k satisfies this argument, right? So it means, I'm going to write it here, L to the power 5 minus L is actually equal to 10 multiplying something, because L is below k, and that we said 0, the claim is true for that, for this guy, and then L was k minus 1 less than k. The claim is true for all these guys, right? So anything that is below k is also true. K is true, and anything that is below k is true. And L is actually below k. L is k minus 1, which is less than k. So L to the power 5 minus L is 10 multiplying b, plus all these guys have 10 multiplying them, right? L cubed plus 10 8L squared plus 10 8L plus 30, right? So this is 10 multiplying everything here, b plus L to the power 4 plus 4L cubed plus 8L squared plus 8L plus 3. This is 10 multiplying some constant p. So the idea was supposed to write the expansion of k plus 1 to the power 5 minus k plus 1 to be 10 multiplying something. And indeed, we've been able to do that. So this is true, right? So for n equals k plus 1, it's actually true. So we've been able to prove that. So the claim is proved. But the other case is this true? Are we okay? Like, is everything right mathematically? You go back and check where you said k is greater than or equal to 0, right? So let's go and argue something. K is greater than or equal to 0, but the L that we picked, L is equal to what? K minus 5. And we said k is greater than or equal to 0, so L is between this guy. Okay, so that is saying that 0 is less than or equal to k minus 1, less than k. But k is actually starting from 0 and above. So when k equals 0, what happened to this side of the inequality? We are supposed to get 0 less than or equal to k minus 1. Now when k is equal to 0, you have 0 minus 1, which is negative 1. And 0 is not less than 1, negative 1. 0 is not less than or equal to negative 1. This is not true. So it means we should start our k from somewhere else. We are supposed to start our k from somewhere else, and then to do that, you are supposed to solve some equation. I did that in a previous video. So you are supposed to pick your 0, equate it to L, and solve for k. So 0 is equal to L is k minus 1. So k is equal to 1. So you solve for another base case where k equals 1. Remember that we solved the base case when k is equal to 0. I mean n equals 0. So you're supposed to solve for n equals 1 as well. So for n equals 1, what do you have? You have 10 divides 1 to the power 5 minus 1. And that is saying that 10 divides 0. So it means that 0 can be written as 10 multiplying 0. And it's the same thing as the base case that we picked. So this is also true, right? So saying this is also true, then we use two base cases. So the base cases that you use are when n equals 0 and n equals 1. Then when you have n equals 1, then you can say that, well, then at the inductive step, then we can claim that k is not, is this, you just do the k greater than or equal to 1, because we did all the way to 1. So that is the only thing that changes here. Then if you're able to come back and change this, then this is true. So the base case, we said this, and then you also show for n equals 1, which will give you 0 is equal to 10 multiplying 0. That is what we just did. And that is true. So when you're able to show the other base cases, it means your claim is true. And that is what we call strong induction, right? So let's look at another problem, and I think this should be the last problem on inductions. Now, given the recursive relation f sub n, which is equal to f sub n minus 1 plus f sub n minus 2 for n greater than or equal to 2, you're supposed to, with f naught or f sub 0 equals 0 and then f sub 1 equals 1, show that for n greater than or equal to 6, f sub n is greater than this guy. In order to get for n greater than or equal to 6, it means you're supposed to solve we have f sub 0, f sub 1. So we are supposed to get f sub 2, f3, f4, f5, f6, and see that when you are starting from 6, because n is starting from 6, right? So f6 or f sub 6 is what we need. Now notice that f sub, using this formula, right? We know f sub 0, f sub 1. Then it means f sub 2 will be equal to f sub 2 minus 1, which is 1, plus f sub 2 minus 0, which is 0. And that's going to be 1 plus 0, and that is 1, because I have this guy to be 0, I have this guy to be 1. Now continue everything. We have f3 to be equal to 2. Actually what we are interested in is f6, so I'm going to write f6 here. So f6, if you have to do for f3, f4, f5, and use those things to get f6. Now if you calculate, f6 is going to be 8. So now we start with our base case. For the base case, n should be equal to 6, because it's starting from 6, right? That is our base case. Now when n is equal to 6, what happens? When n equals 6, f sub 6 is equal to 8, and then it means we are supposed to show that 8 is greater than 3 over 2 to the power 6 minus 1, right? So the n that you have, and this guy is equal to 3 over 2 to the power 5. And this is the same as saying 243 over 32, right? 243 over 32. And if you look at it in this way, you can try to choose it to be maybe 200 over 30. Okay, this is more like a 6 point something, right? 6.7. But then we have 43 and 2 that we left. I intentionally left them. But this giving me 6.7 means if I add a 43 and 2 to both of the numerator and the denominator, these guys will be indeed less than 8. So it implies that f sub 6 is greater than, you can actually point that on your calculator and then try to see that 3 over 2 to the power 6 minus 1. So this is true. All right. This claim is actually true. So once you have your first inductive, your first base case, you use it to prove the P of k plus 1. And then you come back and check for the other base cases. If you don't show the other base cases, your claim is not valid. Like, you've not proved it. That is the principle of strong induction. All right, so suppose, so the inductive step is that you suppose, okay, inductive step, you suppose that for k greater than or equal to 6, so we actually did 6, that is our base case. I'm so sorry this is happening. So we actually did the first base case to be 6, so we just always choose this and work with that. P of k is true, so that is f sub k is greater than 3 over 2 to the power k minus 1, right? Now let's consider this. Consider n equals k plus 1. What happens? When n is equal to k plus 1, what's going to happen here is that you're going to do f sub k plus 1, and by the recursive relation, what will be f sub k plus 1? It's going to be f sub k plus f sub k minus 1, right? So n is equal to k plus 1, you're going to be f sub n minus 1, that is k plus 1 minus 1, plus f sub n minus 2, which is k plus 1 minus 2. So in effect, this is going to give me f sub k plus f sub k minus 1. This is what you have, right? So now having this, I can rewrite this as f sub k minus 1 plus f sub k. Now we've already showed that f sub k is actually true, and then k minus 1 is actually less than k, right? Notice that we started with 6, so we can say that 6 is less than or equal to k minus 1, less than or equal to, less than k. That is where we started, right? So it means anything that is below k is also true. So luckily for us, k minus 1 is less than k, so it means f sub k minus 1 is also greater than 3 over 2, then k minus 1 minus 1, right? So this is saying that this is greater than, because this guy is greater than that, this is also greater than this. So when I sum them, the whole of them, the sum of them is greater than the sum I have here. Okay, so I'm going to have 3 over 2, k minus 2. Notice that this will give me k minus 2 plus 3 over 2, k minus 1, right? That's what I have. Now, if I factor, so it means that f sub k plus 1 is greater than what? Because it is equal to this, and this guy is greater than that. It means that this here is also greater than the whole of that, right? So this guy is greater than 3 over 2, k minus 2 plus 3 over 2, k minus 1. Now this side here is equal to, so this is already greater than, but this side is equal to, when I factor k minus 2 out, 3 over 2 to the power k minus 2 out, here I'm going to get 1, but here I'm going to get 3 over 2. So that when I multiply this guy here, it's going to give me this k minus 1 back, right? So I think it's simple algebra that I'm hoping that you'll be able to do. So this is equal to 3 over 2 k minus 2 into 1 plus 3 halves, and 1 plus 3 halves is actually 5 over 2, right? So I'm saying that f sub k plus 1 is greater than 3 over 2 k minus 2 multiplying 5 over 2, right? Now there's nothing much of a thing that we can do, right? So here all that we are supposed to do is try to create something here. Notice that 5 over 2 is greater than 9 over 4, because 5 over 2 is like a 2.5, 9 over 4 is a 2 point what? 9 will go into that, 1 to 2.2 something, right? So if I replace 5 over 2 by a 9 over 4, then it means that whatever I have here, since this guy here is greater than 9 over 4, everything there will also be greater than 3 over 2 k minus 2 multiplying 9 over 4, right? So then it means f sub k plus 1 is greater than, also this side, because this is greater than this, and this guy now is greater than that. So it means the parent one, that is this f sub k plus 1, is also greater than 3 over 2 k minus 2. But 9 over 4 is the same as 3 over 2 squared. I don't know if that makes sense, but this is true, right? So it means f sub k plus 1 is greater than, now the power here is k minus 1, k minus 2, this is k minus 2, k minus 2, and this is 2, right? So if I sum them, I use indices, and that's going to give me k, right? So this is true because this power that I have here is the same as k plus 1 minus 1, right? So notice that the first problem was f sub n is greater than, the argument we are dealing with is 3 over 2 n minus 1. So here when n equals k plus 1, we have f sub k plus 1 is greater than 3 over 2 to the k plus 1 minus 1. And it follows the same, so here this is n, and this is n. So it follows the same argument, right? So this is true. This is true. So we are done with the claim. Actually, the claim is actually true, right? Everything is true. But the problem is with this something here, because we said 6 is less than or equal to k minus 1 and less than or equal to, so less than k, right? Less than k. Now, when you have k, where is k starting from? That is a problem. Where is k starting from? Actually, let me see how the problem is stated. For n greater than or equal to 6, right? Where is k starting from? starting from 6. So that is what sorry. Okay, so n is actually starting from 0 because I said if you have 6 is less than, yeah, I think that is the same thing. I'm so sorry. So yeah, we said k is greater than or equal to 6, right? So this is what we're dealing with. Since k is greater than or equal to 6, and that we have this argument here. When k is equal to 6, what happens? You have that 6 is less than or equal to 6 in this middle here. 6 minus 1. So you get 6 is less than or equal to 5, which is not true, right? 6 is not less than or equal to 5. So what do we have to do? Solve this equation. Pick this smaller one. 6 equals this k minus 1 that we did. And so it means k will be equal to what? 7. So the base case that we picked, the base case was k equals 6. That's what we showed. And indeed, f sub 6 was greater than 3 over 2 to the power 6 minus 1. So now, since we've been able to solve for k minus 1, we had that k is equal to 7, solve for this as well. So this one was actually when n equals, n equals 6. And since we had k to be 7, solve for n equals 7 as well. And you notice that f sub 7 is also greater than 3 over 2 to the power 7 minus 1. Actually, f sub 7 is actually 13 using the recursive relation, and is greater than 3 over 2 to the power 6. You can check that. So the base cases were supposed to be when n equals 6 and n equals 7. So you use these two base cases and then you show. And by the inductive steps, you show that for k greater than or equal to the last base case you picked, that is 7. And that will satisfy this criteria. That indeed 6 is less than or equal to, we said k is greater than or equal to 7, the new base case we had. And that when k is equal to 7, you have 7 minus 1. And that's going to be 6 is less than or equal to 6. And the equality will hold. I hope this makes sense, right? So yeah, that is all about strong induction. The first thing that you do, the first step is that you first solve as if you are using the normal principle of induction. Then after you are done proving it, you check your base cases, the argument, whatever you said, and make sure that all of them make sense mathematically. And when you get them right, then so be it. But if you realize that some of them are not right, which I think almost all the time that's what you're going to face, then you try to go back and solve for the other base cases and write your proof properly. So if I'm supposed to rewrite the proof, I'm going to start with base cases. You start with n equals 6. You show that is true, and n equals 7. You show that is true. Then you start with inductive step. All right, for any k greater than or equal to 7, so you pick that bigger one. Then you start. That is where the claim will be true. Then the rest of the argument is going to be the same thing that we went through. Everything is correct, right? So thank you, and don't forget to subscribe to my channel if you have not subscribed. Share my video, like it, and also comment. All right, see you.